So it's my pleasure to present today our recent work in 4D printing and 4D microprinting. Before starting, I would like to show you where we are. So we already learned with Thomas where Aachen is in Germany. So we are also in Germany, a bit more in the south, just less than 1 hour in the south of Frankfurt, in the beautiful city of Heidelberg, that it has one of the oldest university. And of course, you are also welcome to visit us. Regarding our research, so I'm a chemist by training, and we are very interested in designing new materials for 3D and 4D printing. Our main tool is light, so you can see that we are also very interested in the more basic background of photopolymerization. Due to my background, we have also some projects in self-assembly and more recently in sustainability. But today, as you can imagine, I will present our recent work in 4D microprinting. I said that our main tool is light, so we print with light. And I would like to just have a short introduction on the light processes that are very important for 3D printing, and especially the difference between 1 photon and 2 photon polymerization. So you are all known, this is very basic, but I think it's very nice to have a fresh start. So we can excite 1 molecule. In the case of 3D printing with light, usually a radical initiator from the ground state to the excited state to generate radicals and to initiate the polymerization. And this is the process that it happens in several 3D printing processes, for example, in DLP that we have already heard before. So we have as a light source just a UV laser or an LED. The resolution depends on the printer, but we are in the micrometer region and we can print macro scale. But we can also use have 2 photon polymerization, which means that we need 2 photons simultaneously for exciting this photoinitiator to induce the polymerization. So if we see already, we compare the energy, so we have low photon energy, but the probability of the effect is much lower because, as I said, we need 2 simultaneously photons at the same point at the same time, meaning that we will only have this photopolymerization in a very small volume. And this is why transfer to 3D printing, that means that we are able to go down in the scale to micro and nano printing. In this case, for having this process, we need femtosecond lasers, usually in the infrared. And as you see, we go down way well below the micron, and of course also with the printing size in the micromillimeter regime. We have heard today already about DLP, so I will have some examples that we have print DLP, but most of the example we have print with 2 photon polymerization, and we will see also how to design these materials. But in case you are not familiar with this method, I have also one animation to show you how does it work. So we start, of course, with our printable material. We focus inside our femtosecond laser. And as I mentioned, due to the non-linearity, due to the lower probability of the process, this photopolymerization is happening in a very, very small volume that we call voxel. And just by moving the focus of the laser or the heat or the printing stage, it depends on the methodology, we can in principle achieve almost every arbitrary geometry with submicron resolution. Applications, so why we want to go so small. So this is very interesting for photonics and microfluidics, and lately this technology is also starting to be very interested in cell life science and micro robotics. So just having a look to the applications, cell scaffolds, micro robotics, microfluidics, you see that the aim or the necessity of have adaptive or smart materials is there. And this is what my group is doing, is trying to develop new smart materials for this type of printing. And within the cluster, within the 3D Matter made-to-order cluster, we have explored different classes of responsive polymers. For example, we have worked with hydrogens in collaboration with other groups, especially with polynipam for the preparation of thermal-responsive microactuators. And we have also explored the well-known liquid crystal elastomers and safe memory polymers. So let me start with liquid crystal elastomers. So as you know, liquid crystal elastomers, they have been exploited at the macro scale for actuators. And also this is a very nice and material and potential applications at the micro scale for micro robotics. So important for having this actuation is that we need to induce a transition from the liquid crystalline state to the isotropic state. So we need to start from an order state, and therefore alignment of the monomers is very important. Very often it's done via rubbing structures, but when we want to go to complex and to the 3D, we want methodologies that allow us to align also in the third dimension. So that was our first step, to enable the technology to have the freedom to align liquid crystals while printing. And that was done by Alexander Musinger, that is a PhD student in the group of Martin Wegner. That was a collaboration with the KIT, also in Germany. So here we have a sample holder that it has an electrodes that allow us to apply an electric field and induce the order of the molecules. And then what we do while printing is fix this conformation. So which material have we employed for that? So the material is not very special. There are the well-known liquid crystal mesogens with 1 or 2 acrylate groups allowing us the printing. But very important actually in this formulation was this E7 mixture. So this E7 mixture is a liquid crystalline at ambient temperature that is kind of a guest in the system. So it allows us to decrease the viscosity of the monomer, but it also, due to the liquid crystalline properties, helping to have good alignment at lower electrical fields. And yes, using this method, Alex could print very nice structures that it has, if I don't remember wrong, until 9 different orientations. You see that when we induce this transition, we have this bending. So that was, again, a very nice first achievement. But if you have a look to the temperature, we need to induce this transition due to the high crosslink density that was very high. So next step was, can we do this with light? Then we can have also a spatial control. So that was the task of my PhD student Li Yun-Su. And when we started, one thing, okay, that's quite straightforward. We add to the formulation some photoabsorber, some dye, and then we should have light response. So unfortunately, it was not so straightforward because, as you can imagine, we are printing with light. So having this photoabsorber was hindering this low probable photopolymerization, and that was not so simple. But she came up with a very nice approach that I will try to explain here. So you remember that I told you before that together with the monomers, we have E7 mixture in the formulation that is kind of a guest. So the idea here was, okay, so we continue with our printing methodology that is working, and then in the development step, we exchange this E7 with a dye, because we have, of course, some space from the molecules that they were already in the 3D printed structure, and then we don't have any more any constraints in the printing wavelength. And then she managed to incorporate not only the well-known isobenzenes, but also other dyes that absorb more in the red or even close to the infrared, such as the DASA and the Sudan blue. And this also opens new opportunities when, for example, for biomedical applications, you don't want to go to UV or blue light. So in this way, you can see that she printed these actuators as a proof of principle, introduced different dyes from the 3 classes, and now we have the option to either excite, depending on the dye, with different wavelength, this actuation without going to these high temperatures. And if you have a look to the absorption, you see that the absorption from the isobenzene is quite orthogonal to the DASA or the Sudan Blue. So that's the next step. That will be very nice if we could have especially resolve actuation of different parts, so going to multi-material. Of course, with this approach of developing is not possible, so we are still not there, but we have a start in this direction at the macro scale. That's a recent work from Philipp Mainik. And here what we did was to print these multi-material structures using DLP. So first we printed an elastomer as a passive material, and then we introduced the liquid crystalline, doped with the different dyes. You see there already the 3 different colors, and here the direction of the alignment is in the direction of the beams. So you see that they have different absorption. So now when we use, for example, blue LED, all of them are actuated. If we go to the red, only the Sudan blue, and this one more green, black one, the infrared, is actuated. And if we go to higher wavelength to 850 nanometers, we can only actuate one. So the next example that I have here for today is safe memory polymers. We have heard already, or we have seen some examples of safe memory. So here what we did with Christoph was to try to learn more about the design of materials for light-based 3D printing, and then we had the target to try to find one system that is very versatile that we can use for macro-scale printing using DLP and also with micro-scale. So I told you at the beginning that, of course, we have this low probable. So then for 2-photon laser printing, usually we need a higher density of cross-linkable groups. And that was the exercise to play with the cross-linker and main chain builder that will allow us the safe memory response. So how does it work? We have our printing formulation, as you can see here, our Norbornil, that it acts as a main chain builder, and the crosslinker. We have one flexible one and also one stiffer one. And that was very important to achieve the right mechanical properties and response. And as I said, to adapt its formulation for macro and micro printing. So after printing, we create this network, having the isobornil as a main chain builder, and at room temperature, we have a stiff material. Then we heat above the glass transition temperature. We have something flexible that we can program. We cool down to fix the geometry, and then by heating, we can recover. So the typical one-way safe memory polymers. So just by having the right formulation, we could print structures at the macro scale using DLP, some simple ones, some having more overhanging, or this platform that was not new. Of course, it has been done before with other materials, but here the new thing at that point was to really transfer to the micro scale. So you see that we could also print the same geometry at the micro scale, so very tiny, around 20 microns, and also print these micro boxes that we can close on, even encapsulate some spheres. So as you can imagine, the programming is a bit more tricky at the micro scale because we are really with tiny objects. And what we did was to use a preheated metal block that to gently push for the programming. You can see here how we have done with this geometry. So this is the starting point, then after pushing, and then the recover. So again, a nice result, but we were still not really completely satisfied about this, because when you use temperature, you have a global recover. And the idea here, I think you already realized that we're a big fan of light. Can we have also spatial control in the safe memory? And this is what we have done in next work. So using the same formulation, we incorporate azobenzene as an absorber. And what we have here is a flower. We have programmed in the closed form, and now we can have the recovery spatially controlled because we have the photothermal effect by irradiating the printed structure with the absorber. And we have also here another example. This is still at the macro scale. It works nice. It's a bit slow because, of course, we have the diffusion, and we believe that at the micro scale we can go to faster response. Okay, so now I would like to use the last minutes to show you a recent example. So after printing with the more, let's say, classical way of responsive polymers, liquid crystal elastomers and shape memories, we thought, okay, what else can we do? Can we expand a bit the response? And again, taking inspiration by nature, you know, natural system can grow. So a tree can grow, we can also grow, and we increase in size, in weight. Okay, there is one way that maybe we get also old, but we stop here. So the trend is always increasing in size and weight. So can we do that also, or mimic that by 3D printing? So again, coming from my background as a polymer chemist, so here we exploit alkoxamine chemistry. So here the formulation is very simple. We have a dye linker and a tempo that very often is used as a radical quinter, but this tempo has a photopolymerizable group. So we can incorporate. Then we can use this alkoxamine for chain extension, so we can grow, expand our object, and we can also, if we add an excess of tempo, have nitroxide exchange reaction with the idea to change the cross-linking density. So here now we have two properties that we can tune, size and the mechanical properties, and this is how we have done. So I don't have much time to go in detail in the formulation, but here you can imagine that if we have a radical quencher, we need to optimize very nicely the photoinitiator and also the cross-linkable density. We prove the incorporation of the alkoxamine and the chain extension via IR via top sims. And here is the result. So this is the micrometric gecko that Christoph printed. When we put it in a solution with an extra tempo, so you see that apparently nothing changed because we still have a lot of acrylate cross-linkable groups. The Young modulus decreased a bit due to the decrease of the density, but not much. But that it was more impressive is when we expand with styrene. So here you can see that's the starting point. After 2 hours, the gecko grows. After 4 hours, even more. But the gecko is not only growing, because we are incorporating styrene as stiffer polymer. We have also quite a change, a dramatic change in the Young modulus. So we can go to the gigapascal regime. And this is not only happening with the gecko, that happen also with other geometries, and you see that we can keep also quite nicely the minimal features, and here is a GIF that you can give you the impression of this growing, of this change in volume. So that's all the examples that I had for today. Just to conclude, I would like to thank you again, the organizers, the group, the whole team for the great work, and especially to Christoph, Philipp, and Li-Yun for pushing this for the micro printing, all the funding, and all of you for your kind attention. I will be very happy to take your questions.